The same technique used to derive the RK2 methods can be expanded to derive higher-order Runge-Kutta methods. For example, an RK3 method will include three AK products, where each of the Ks is an evaluation of the function f from the defining equation for the initial value problem. In general, K1 is evaluated at xi and yi, K2 is evaluated at some different point, xi plus some fraction of h, and yi plus some fraction in the y direction. And K3 is evaluated at a different x location, and at some position in y that could be calculated from a combination of K1 and K2. The third-order Runge-Kutta methods, or RK3 methods, are derived using the same technique that we used to develop the RK2 methods. That is, we set this equation equal to the Taylor series, and then equate like powers of h just as we did before. In the case of the RK3 methods, that provides us with 6 constraints, but we have 8 constants, which are colored red here: A1, A2, A3, B1 and B2, C11, and C21 and C22. That leaves 2 additional degrees of freedom, which means that there are an infinite number of possible RK3 methods. We'll look at just 2 of them. What's known as the classical RK3 method combines f evaluated at xi, f evaluated at xi plus 1/2 h, and f evaluated at xi plus h. Heun's RK3 method combines f evaluated at xi, f evaluated at xi plus 1/3 h, and f evaluated at xi plus 2/3 h. Based on the derivation using the Taylor series, all of the RK3 methods will have global truncation error of order h cubed, and they only require multiple function evaluations of f, but do not require calculating derivatives of f. If we use the same technique to derive higher-order RK methods, we will always arrive at fewer constraints than we have coefficients. We'll look at just one RK4 method. This is called the RK4 method. It combines a function evaluation at xi, a function evaluation at xi plus 1/2 h, another function evaluation at xi plus 1/2 h using a different estimate for the y coordinate. The first one is derived using K1, and the second one is derived using K2, and then a function evaluation at xi plus h. This is the classical RK4 method, and when people say Runge-Kutta or RK4, they're usually talking about this particular Runge-Kutta method. The global truncation error for this RK4 method is of order h to the 4th. Butcher's RK5 is probably the most common RK5 method. It actually involves 6 and not 5 function evaluations, but only 5 of the 6 are summed. Notice K2 is missing from this summation. K2 is, however, used to evaluate K3, K4, and K6, and appears implicitly in K5 through the K4 term. Butcher's RK5 involves a function evaluation at xi, 2 function evaluations at xi plus 1/4 h, a function evaluation at xi plus 1/2 h, a function evaluation at xi plus 3/4 h, and a function evaluation at xi plus h. In fact, the reason that this is really an RK5 method and not an RK6 method is because the function evaluations K2 and K3 can actually be combined. Dividing them up this way simplifies the notation. Runge-Kutta-Fehlberg methods are methods that have an adjustable step size. With using Runge-Kutta methods, we cannot guarantee a certain global accuracy, but we can estimate the local accuracy by comparing 2 methods of different accuracy. For example, we could calculate y at xi plus 1 using an RK4 method, and then compare that to a more accurate estimate of y at I plus 1 using an RK5 method. If the difference in the estimates between these two is large, then it's likely that neither one of these is a great estimate, and we should go to even a higher order Runge-Kutta method if we want to improve the accuracy. Another way but we could also improve the accuracy by simply reducing the step size h and repeating the calculation. Unfortunately, this requires a lot of function evaluations at each step, because if we were to use the classical RK4 method and, say, Butcher's RK5 method, we would need a lot of function evaluations because these all have different k's. The Runge-Kutta-Fehlberg 4-5 method uses a different RK4 and RK5 method than the ones that we've already presented, such that the k's that are used in the RK4 method are actually contained within the RK5 method. This reduces the number of function evaluations. These k's and the coefficients that define them are given on pages 320 and 321 of the methods textbook. For all Runge-Kutta-Fehlberg methods, two RK methods are required, one with a lower order, p, and one with a higher order, p plus 1. The difference between the estimates for the order p and order p plus 1 methods is used as an estimate of the local accuracy. If the error in the RK method of order p is too large, then the step size is adjusted according to a formula that includes a tolerance and an adjustment parameter alpha. RKF45 uses alpha equal to 0.84. Here, the difference between y at I plus 1 tilde and y at I plus 1 is intended to represent the local truncation error, estimated by the difference between the lower order and higher order RK methods. Together, the Taylor methods and the RK methods make up the one-step methods. In the next video, we'll introduce the multi-step methods.